Welcome. Let us start off today's class by considering two problems. In the first problem, we have a sphere like this. You can think of it as the sun or some other sphere of gas, and the sphere has mass m and radius r, and it is in gravitational equilibrium. So, if it is in equilibrium, the sphere satisfies virial theorem. Okay. So, this sphere is made up of hydrogen gas. We shall assume that it is made up of ionized hydrogen gas and it is in virial equilibrium. Now, this sphere in virial equilibrium, it will have some virial temperature. We shall come to this. It has some virial temperature, and this sphere we will assume that it also emits radiation from the surface. And the temperature, at a temperature T effective, which is a fraction f of the virial temperature. So, the luminosity of this object is 4 pi sigma r square T effective to the power 4. So, the first part of this problem, this is the information given. So, the first part of the problem is to estimate the virial temperature of this object A. So, let us call it A. What is the virial temperature of this object? So, the virial temperature Tv, and how does this scale with the mass of the object and the radius of the object? Okay. Now, we know, so let us address this question. So, we know that if an object is in virial equilibrium under its own self gravitational force, then the average kinetic energy is equal to the total energy in magnitude, and it is half the potential energy. Okay. And here we will also assume that the potential energy is minus g m square by r. Okay. So, we want to find out how does the virial temperature depend on the mass and the radius of this object. Okay. So, we know that in virial equilibrium, the kinetic energy here is essentially the thermal energy ETH. So, this is going to be equal to half of this value. So, half of this value means it is going to be g m square by 2r. And this is an ideal gas, ionized hydrogen. So, we know for an ideal gas the thermal energy is 3 by 2 into the number of particles. The number of particles is going to be the total mass of the object m divided by the mass of the hydrogen atom mH, and there is also the mean atomic mass of this that you have to take into account, or another way of thinking of it is that every hydrogen atom essentially contributes 2 particles, not 1, because it is ionized. So, there will be a or you may say that the mean atomic mass is half. Okay. So, there will be a factor of half here, that is the number of particles, it is the mass of this object divided by half the mass of the hydrogen atom. So, N K, the Boltzmann factor K B into T virial, that is how the internal, that is how the virial temperature is defined. The internal energy is written in terms of the virial temperature in this way, it is basically 3 by 2 N K T. N is the number of particles, K B is the Boltzmann constant into T. So, this straight away gives us the dependence of the virial temperature on the mass and the radius. So, the virial temperature is equal to so, let us see how much is it equal to. So, the virial temperature is equal to, one factor of m cancels out, it is equal to G m into the mass of the hydrogen atom these factors of 2 will cancel out, and if I bring this onto the left hand side I will get a factor of 6. So, G this divided by 6 into the Boltzmann factor K B into R. I hope we have got it correct, right? Let us just check. So, M right. So, that is the virial temperature, it is essentially proportional to the mass of the object and inversely proportional to the radius of the object. Okay. So, that is the first part. The second part, we would like to calculate the luminosity of this object. And I have told you that this object, that we are assuming that this object emits from its surface as if it were a black body of temperature, of this effective temperature, which is a fraction, some unknown fraction f of its virial temperature. Okay. In principle, if it is optically thick and the temperature is the same throughout, then it will be exactly equal to the virial temperature, but it may not be exactly optically thick. Okay. So, let us just use this and see how the luminosity depends on the mass of the object and the radius for such an object. Okay. So, the luminosity L is equal to 4 pi. So, let me just keep the factor of 4 pi as it is, 4 pi, and then we have this Stephen Boltzmann constant sigma, and then, so let me write those factors down, 4 pi sigma, and then we have r square then we have this T effective to the power 4, which we can write in terms of the virial temperature. So, we have so the luminosity can be written as some constant C, whose value you can work out by taking all the coefficients over here, all the constants, into f to the power 4 in what's the dependence on the mass. We are interested in the dependence on the mass and the radius. So, the dependence on the mass is m to the power 4 by r square. Okay, so that is the second part of the problem. The luminosity is proportional to the mass to the power 4 divided by r square. Okay. The thermal energy is proportional to the mass square by the radius, the virial temperature mass by r, and the luminosity mass to the power 4 by r square. Now, this object, when it radiates, it loses energy. Okay. So, the total energy and the thermal energy are equal in magnitude. So, you can just equate the loss, and the thermal energy will increase if it loses energy. We have already discussed this. So, we can now equate the rate of loss in energy to the luminosity. Okay. So, let us do that, and what we get is d by dt, the rate at which the thermal energy is lost, and the thermal energy is g m square by 2 r. Now, when the energy is lost, it is only r which is going to change, the mass remains fixed. So, it is essentially 1 by r and this is equal to C f to the power 4 m to the power 4 by r square. So, I can absorb these coefficients g m square by r into this constant c and redefine another. So, I can have another constant which is 2c by g m square by g, basically 2c by g, and what I will get is that d by dt of r minus 1 by r square is equal to, so this was c, let us call that give it some other name, let us call it c bar. This is equal to c bar, and we now have m squared over here, f to the power 4 m squared by r squared. So, this 1 by r square cancels out, and the problem is that when this, so the question is as follows: when this loses energy, its thermal energy is going to increase, its potential energy is going to get lower and lower. So, this thing essentially contracts, and we want to find the rate at which it contracts. We want to find the solution to r as a function of time by solving this equation, right. So, which now we can do straight away, it is quite simple. So, r is equal to, so r naught, which is the starting value of the radius, minus c bar f to the power 4 m square into t. Okay. So, that is how the radius changes with time, where you can work out exactly what the numerical value corresponding to c bar is by just backtracking a little, and m is the mass of the object, f is the relation between the effective temperature and the virial temperature, t is time. So, the time at time t equal to 0, the object has some radius r naught, and r will be the radius at some later time t. Okay, so the object essentially contracts, and the entire object according to this collapses at a time t equal to r naught by c bar f to the power 4 m squared. Okay. So, having done this, let me now leave the remaining problem to you. So, you have to estimate, the rest of the problem is left for you. You have to estimate the time it takes an object of the mass of the sun and the radius of the sun to collapse. How much time in this model, how much time will it take to collapse to r equal to 0, assuming f equal to 1. Okay. When you do this, you will find that this is a ridiculously small time. Okay. So, the question is then why? How come you get such a ridiculously small time for such a massive object to radiate away all its energy? Okay. And you can actually work out the reason if you estimate what the starting T virial is. Okay. If you estimate the virial temperature to start with, you will find that this is much higher than the mass than the actual surface temperature of the sun. Okay. So, to get an idea of what would happen to the sun, about the Kelvin Helmholtz time scale for the sun. So, to get an idea what would happen for the sun if there was no source of nuclear energy, you would have to change the value of F. Okay, so change F. So, change F so that the effective temperature comes out comparable to 5800 Kelvin, which we know to be the surface temperature of the sun. Okay. And again estimate the time it would take to collapse. Okay. So, these are parts of the problem that I leave for you to work out. I have done a part of the problem, I leave the rest of the problem for you to work out. You have to essentially put in numerical values and go through this exercise. I hope the problem is clear. Okay. The next problem that I am going to discuss is, again I have mentioned this problem, it is not something new. The problem is as follows. We will look at nuclear. So, the previous problem had to do with the virial theorem, the next problem has to do with hydrogen burning. So, the problem again has two parts. The first part, we know that the temperature at the core of the sun is around 1.6 into 10 to the power 7 Kelvin. So, let us estimate the average temperature, average energy of a particle, of a proton at this temperature. Okay. And we know from kinetic theory that the average energy of a proton at this, of a particle at this temperature is 3 by 2. So, the energy of the typical energy of such a particle, kinetic energy, is of the order of 3 by 2 the Boltzmann factor into the temperature. So, this will give us a, so the particles inside have a Maxwell-Boltzmann distribution of velocities, and so the kinetic energies also have a spread. The typical energy, kinetic energy, is of the order of 3 by 2 kBT, the average kinetic energy, and you put in the values. So, three by 2 into 1.38 into 10 to the power minus 23, that is the Boltzmann factor, into 1.6 into 10 to the power 7. That is the value of the temperature, and this value, if you put in these values and do the calculation, it comes out to be 3.2 into 10 to the power minus 16 joules. That is the kinetic energy of the protons. Okay. Now, the next question is that for the nuclear fusion, for hydrogen burning to occur, the first step is the PP collision. So, we need two protons to collide to form a deuteron, right. So, we have two protons, and we know that at large scales there is the Coulomb repulsion between any two charged particles which have the same charge, and it is only if they can approach within a distance r naught of the order of 1.4 into 10 to the power minus 15 meters will the of this order will the strong interaction come into play, and they will then be able to merge and form a deuteron. Okay. So, the question is, what is the potential energy of two protons at this distance? So, the kinetic energy has to be equal to this amount if you want the protons to approach, to overcome the Coulomb potential and approach each other to such a small distance where they can be become bound by the strong interaction. So, let us estimate the potential energy of this. So, the potential energy of such a configuration is minus 1 by 4 pi epsilon naught into the charge of the proton, which is the same as the charge of the electron, square E square by r naught. So, here again let us put in the values, and we have the 1.6 into 10 to the power minus 19, that is the charge of the proton square in all in SI units. So, that will be in coulombs, divided by 4 pi into epsilon naught, which has a value 8.9 10 to the power minus 12 into the distance, which is 1.4 into 10 to the power minus 15, all in SI units. So, you put in these numbers and the potential energy comes out to be of the order of minus 1.6 into 10 to the power minus 13 joules. Okay. So, this simple estimate can compare the typical kinetic energy is 10 to the power minus 16, whereas the potential energy is 10 to the power minus 13. So, it is roughly, the kinetic energy is roughly 1000 times less. Okay. And this is the problem which I had mentioned earlier. So, inside the sun the protons do not possess adequate kinetic energy for this collision to occur and for the reaction to proceed, if you think of them as classical particles. Okay. But when you treat them as waves, there is a probability that they can tunnel through this barrier and for the reaction to take place, and it is only because of this that you have the nuclear burning, hydrogen burning going on in the center of the sun. Okay. So, having discussed these two problems, let me now move on to the topic of the remainder of today's class, the remaining part of today's class. So, we are going to now move on to discussing the structure of stars, stellar structure. So, this is what is called stellar structure. So, we already have some idea about this. Now, in today's class, I am going to introduce the equations, the basic equations that govern this. So, this the structure of a star. We think of a star as a ball of gas, a spherical ball of gas. Okay, that is the starting point. So, every star is essentially a spherical structure like this, self gravitating spherical structure. So, it is bound by its own gravitational force, and it is by and large, most stars are hot gas, they are plasma, ionized hot gas. Okay. So, the first, there are 4 equations governing the structure of a star. The first equation is the equation of hydrostatic equilibrium. Okay. So, it is the equation of hydrostatic equilibrium. And we assume that the star is in a static configuration, it is neither expanding nor contracting. We also ignored the rotation of the star. Okay. And for such a fluid, we know that for any part of the fluid, the pressure gradient across the fluid will balance the acceleration or the force per unit mass. That is the main consideration. So, if I consider any small element of this fluid, the pressure gradient across the fluid must balance the force per unit mass of the fluid. Okay. So, here this fluid element, every fluid element is being pulled inwards by gravity. Okay. So, this is spherically symmetric, and every fluid element is being pulled inwards by gravity. The gravitational acceleration acts to pull this fluid element inwards. So, there has to be a pressure gradient. So, the pressure inside has to be more and the pressure outside has to be somewhat smaller, and the difference in these pressures is what balances the gravitational attraction.
So, isn't there a factor of rho here?
Factor of rho, right, there is a factor of rho which I have missed out. So, it is 1 by rho, right, thank you. Okay. So, everything here is spherically symmetric, and so things are only functions of the distance from the center, the whole thing is assumed to be spherically symmetric. So, we can now write this equation as dP dr okay, minus 1 by rho plus the acceleration per unit mass. Okay. So, the question is how much is the acceleration per unit mass. Now, we know that if I have spherical symmetry, only the mass inside this, the total mass inside this is going to contribute to the acceleration of this fluid element. Okay. So, this is going to be equal to minus the gravitational acceleration is g mr by r square is equal to 0. Okay. So, we finally have the first equation, which is essentially this, and I will write it in a slightly different way. So, the final equation that is the equation of hydrostatic equilibrium is essentially dP dr is equal to minus G mr into rho by r square. Let me tell you that mr is the mass within. So, we are looking at a distance r away from the center, and mr is the mass. Let me draw a picture which we can use repeatedly now. So, this is my star, and we are looking at a distance r from the center, and m of r is the mass within this sphere, mass within this. Okay. So, that is all that contributes to the gravitational acceleration over here, and this is the equation for hydrostatic equilibrium. Okay. So, that is the first equation. The second equation that governs stellar structure is the mass distribution equation. So, the mass, we know the mass within a sphere of radius r, we know that this is the integral of the density 4 pi r prime square into rho r prime dr prime. So, what we are doing is we are considering shells like this. So, the thickness of such a shell is dr prime, and the mass inside that is 4 pi r prime square rho r prime. So, this equation can also be written in differential form, which is dmr by dr is equal to 4 pi r square rho r. So, this is the equation that governs the mass distribution. The third equation that is of stellar structure So, the third equation in stellar structure is the flow of energy. Okay, so it is essentially the flow of energy. Okay, so the third equation is the So, let us go back to this picture. Now, let us say that the luminosity at a distance r is L of r. Okay. And the luminosity at a distance r plus delta r is L of r plus delta r. So, the difference, so let us just calculate the difference in flux between energy flux between here and here. Okay. So, the difference in energy flux between this and this is the luminosity. Okay, we can calculate the difference in luminosity. The difference in luminosity is the total radiation that is coming out from this surface. Right, total radiation coming out from this surface. Okay. So, the difference in the total radiation coming out from these two surfaces, so that is the energy which is generated in this shell. Okay. And the energy that is generated in this shell we write as the volume of this shell. So, the volume of this shell is 4 pi r square into delta r into the density that will give you the mass inside this shell. So, into the density rho r into the energy generation rate, okay, or the emissivity of this material. So, epsilon r. Okay. So, that is the amount of energy generated per unit mass of this material. Okay. So, this gives us the equation that dl dr, how does the luminosity change as we go out from the sun, and dl dr is equal to 4 pi r square rho r into epsilon r, where epsilon r is the emissivity. Or the energy generation rate. And this is something that we discussed just in the last class, in the previous lecture, where we discussed nuclear burning. So, I told you that the energy generation rate is proportional to rho. So, epsilon, this energy generation rate, is proportional to the density into T to the power 4 for the PP chain, right. So, the energy generation mechanism in any star is through nuclear burning. That is the only source of energy generation. Okay. And we saw that there are two processes by which this nuclear burning can occur. One is the PP chain, where two protons collide to give you helium 4, and the energy generation rate is proportional to the density into T to the power 4. Okay, this is the rate per unit mass, that is proportional to density to the power 4. There was another mechanism which was the CNO cycle, and for the CNO cycle this was proportional to rho T to the power 15. I told you this also. Okay. So, when you solve for the stellar structure, one has to also take into account the fact that there is energy being generated in different parts of the star. The energy generation rate is more effective in the center, where the density is high and the temperature is high. It is less effective in the outer parts, where the temperature is low and the density is also low. Okay. So, one has to simultaneously incorporate this, and that goes into determining how the luminosity changes as we go away from the center. Okay, that goes into here, and we have written this as a function of r, because both the density and the temperature are just functions of r. Okay. In reality, it is essentially, if you look at the physics behind it, it is a function of the density and the temperature, but since the density and temperature are themselves functions of r, when you solve the stellar structure, you have to essentially can think of it as a function of r. Okay. So, that is the third equation. The fourth equation is the temperature. So, we need to know the temperature profile So, how does the temperature change inside the sun? And this, how the temperature changes, is essentially determined by the energy transport mechanism. Okay, so this is determined by the energy transport mechanism. And there are two energy transport mechanisms that are active inside stars. The first one is radiation. So, you can have radiative transport. So, in radiative transport, what happens is that the photons they get absorbed and re-emitted, and they slowly make their way across the sun, okay, and they diffuse. Okay, so this is a diffusion process. It's a random walk. We have discussed this. So the photons slowly make their way. It's a slow progress through the sun. Okay, so this is the radiative transport. There is another mechanism which is also at play inside, which can also be at play inside stars. The other one is convective transport. In convective transport, fluid elements move, and these fluid elements carry the energy. And so the energy transport and the temperature distribution in the sun, the temperature gradients, are determined by which of these two processes is active. It depends on that. Okay, and you can have two possibilities. So the radiation, you can have the energy being transported through radiation, or you could have energy being transported by the motion of the fluid elements themselves. So there is a competition between these two mechanisms, and we shall discuss the criteria when which one will be operational. Okay, but first let us just look at this. So in today's lecture we shall just consider the radiative transport. Okay. So we proceed as follows. Let us consider a shell of the fluid. So two different radii, a distance delta r apart, where okay, delta r is the mean free path of the photon inside this. Okay, inside the sun, and the mean free path we know the mean free path in any medium. The mean free path we know is 1 by the absorption coefficient alpha, or we can write it as 1 by the absorptivity or opacity into the density. Okay. So, this is the absorption coefficient per unit volume, right. That is how we had introduced it, alpha, and kappa is per unit mass. Okay, so, kappa is also called the opacity. And it is related to this alpha which we have been using, which is the absorption coefficient through the density. Okay. So, let us consider two regions, two shells, a shell of thickness delta r, which is of the order of the mean free path inside the star. Okay. So, you can think of the photon essentially propagating from here to here and then getting absorbed or scattered. Okay. Now, let us calculate the energy flux which is incident, which is being radiated by this surface. The energy flux being radiated out from this surface is, okay, we will call this 1, we will call this 2. The temperature here is T1, the temperature here is T2. Okay. So, the energy flux that is being radiated out is 4 pi the flux is going to be sigma T1 to the power 4. That is the flux per unit area, how much energy is going outwards, and that is 4 sigma T to the P1 to the power 4. Okay. The energy flux which is incident in this direction from the upper surface is going to be T2 to the power 4, right. So, the difference of these two, where T2 is less than T1, right, we know this, as you go out the temperature goes down. So, the difference in these two gives me the net outward flux, which is the luminosity. So, if I multiply this with the area 4 pi r square, I get the luminosity at a distance r, right. That is the luminosity at a distance r. So, the photon which leaves from here propagates only this distance typically and then gets absorbed again. The photon that leaves from here propagates this distance and then gets absorbed again. Okay. And the net flux over here, net luminosity over here, is the difference in flux into the area, which is 4 pi r square into sigma, the Stefan-Boltzmann constant, T1 to the power 4 minus T to the power 4 T2, and T1 is greater than T2. Okay. So, this is an estimate of the flux net luminosity at any point. Okay. And so, we can write this as approximately equal to four pi r square into sigma into the derivative of T to the power 4 into delta r. Right, that will be an estimate of this quantity, and the mean free path we know is much smaller than the radius of the sun, very small, it is of the order of millimeters. So, this gives us the luminosity. Okay. And we can invert this relation. So, let me invert this relation to get the temperature gradient inside the star. So, the temperature gradient inside the star is equal to, so what we are doing is we are differentiating this and then taking all the factors onto that side. So this will be equal to the luminosity at that point divided by, I will get a factor of 4 when I differentiate this. So I will have 16 pi r square, the Stephen Boltzmann constant T cube. So let me write it like this: 16 pi sigma r square T cube, and then I have 1 by delta r, and delta r we know is the mean free path, which is 1 by kappa rho. Okay. So we have 1 by delta r, so we have to multiply with kappa and rho. This gives the temperature gradient in the sun, in a star. This is an approximate formula that we have derived. Our calculation here has been rather approximate. If you do a more detailed exact calculation, what you get, this is approximate. If you do a more detailed calculation, what you get, instead of 1 by 16, you get 3 by 64 pi sigma r square T cube L r kappa rho. Okay, this is the temperature gradient. Okay, so this completes the 4 equations which one has to solve in order to determine the structure inside a star. Okay, let me just tell you what this equation tells us. This equation essentially tells us, you can look at this equation. So if you want to have a higher luminosity at a certain point in the star, so you want the luminosity here to be high, then the temperature gradient over here should also be large. Okay, or given the same luminosity, if the opacity increases, then again the temperature gradient has to be larger. For the same luminosity at this point, if you have a higher opacity, then the temperature gradient has to be larger. Okay. So let me now summarize what we have done. To determine the structure of a star, one has to simultaneously solve these 4 equations for the material inside the star. Okay. Now we today discussed only one energy transport mechanism. In the next class we shall discuss about convection, and then also discuss how one goes about solving the stellar structure.